Okay, thank you all for coming along to my talk. My name is Noel Welsh. I am a consultant at Underscore, which is a global Scala consultancy. Today I want to talk to you about differentiable programming, which is the idea of deep learning, and functional programming and how they're related. So the goals for my talk are firstly to show that deep learning isn't really so hard. You might have heard of deep learning. It might seem like a dark, black art to you. You don't understand how it works. I want to show you that the basic ideas are not all that complicated. I want to show you that, in fact, the basic ideas are very similar to what we do in functional programming. It's all about composition. And I want to look at some of the algorithms, the core algorithms behind it, and hopefully you will leave thinking that you could implement it yourself. I'm not saying you could implement a production system yourself. That's a lot of work, but you could certainly implement a little toy yourself, given a day or two, and do some useful things with it, maybe have some fun. Before we get into that, let's just talk a little bit about what deep learning is. So what is deep learning useful for? Well, it's useful for stuff like this, which is always great fun. There's a few of my photos that I took in Rome. We have the Emperor Marcus Aurelius as a dog. The stylized version of a statue of the dying Gaul, and a tree, which has gone a little bit furry. So this is one of the kind of fun applications of deep learning, mucking around with pictures, but there are many more commercial applications, such as voice recognition, the thing that's in your phone that recognizes your voice, and image recognition, stuff that tags people when they're in photos, or pulls out street signs and so on for Google Maps. That's all done via deep learning these days. So that's what deep learning is useful for, but then what is deep learning? What are the core ideas here of deep learning? And what deep learning is all about is supervised learning of parameterized functions by gradient descent. Right, simple, right? Yeah, okay, so that's actually like a whole bunch of buzzwords. Although we did have one person who said it was simple. Who said it was simple? Is you? Okay. For everyone else, let's unpack some of these buzzwords and see what they all mean. So there were three, and we're going to look at them. Firstly, parameterized functions, then supervised learning, and then gradient descent. What do I mean by this? So, parameterized functions. We'll start with a function. You give this function a value, x, you get back the sine of x. Hopefully a very familiar function, and we can plot a picture of it, x versus sine of x, and we get something that looks like that, the familiar old sinusoid. Okay. Now, there are many ways we could change this. We could make it sinusoid bigger, up and down, the amplitude. We could change the period. We can make it tighter. We can make it looser. And there's ways we can change the shape that we get. And what we might call those are parameters that we can manipulate. So, for example, here we have a parameter which we call theta, and we choose a particular value of that parameter, and we get back a function. So this is what I mean by parameterized functions. It's basically functions returning functions, something that's quite familiar in functional programming. And in this case, what we're manipulating is the period. And this gives us this parameter, changes this parameter, gives us a family of functions. So we change the period, so the period is smaller, and we get a tighter function. We change the period, so the period is bigger, and we get this looser function here. So our choice of parameter, our period in this case, changes the function we get. That's all we're trying to do here. All right. So on to supervised learning. Not all deep learning is supervised learning, but it's the most common paradigm. And the idea here is about choosing parameters in some parameterized function to fit some data. So what do I mean by that? So let's say we have some data here, points that look suspiciously like a sinusoid, maybe even generated by one. And then what we might want to do is say, how can we choose that parameter, that period, to best match or fit this data? So here's like one function we could choose, very small period, doesn't look like it fits too well. Increase the period, it's better fit. That looks pretty good. That's probably too big, and that's definitely too big. So we can see that changing this parameter gives us a different function and a different choice that is going to fit the data, or sort of match up with the data in a different amount. So when we come to do this on a computer, of course, we need to have some formal way of defining these things. What does it mean to change the parameter? How do we actually go about changing the parameter? What does it mean to fit the data? And so we'll look at these next, and this is where gradient descent comes in. So the core idea with gradient descent is to algorithmically choose the parameters. And what we need to do with this is firstly define what it means to fit the data. How good is a particular choice of parameter? And the way to do this is choose a particular parameter here, and then draw a line from the data to the function. And that gives us a measurement of error. And you can add up all these little errors, all these distances. You normally use squared distance because it's just a little bit more convenient to work with. And you get some kind of number that tells you if that number is small, then it's a good fit. And if the number is big, it's a bad fit. And if we have lots of different values of this parameter of this period, we could plot out a curve that looks like this. And you can see there's a nice big dip there, which, would you believe it, is the sinusoid that generated the data with a little bit of random noise added. And you can see the harmonics around it are reasonably good fit. And then as you get further away from that choice, you get worse and worse. And so we might think about this if we chose some choice of period, some of that parameter, randomly, then the way we could improve it is we could just roll downhill, down to some minimum. We don't have to get the best choice, but we can certainly, might not get to the best choice, but we can certainly improve it just by going downhill. And formally, what we're doing here is we need to calculate the derivative of what is called the loss function with respect to these parameters. So as you may remember from calculus, if you did calculus, the derivative is just the slope, so that's telling us which way downhill is, and the loss function is just a fancy schmancy term for this distance that we're trying to decrease, this error that we're trying to decrease. And we put this in symbolic notation. We get something like this. We get the data, take away the sign of the data, square it all, because it's just more convenient to work with. And then we can do a little bit of calculus, and you get the derivative of the loss function, and then away you go. These details don't really matter. That's enough to tell us, calculate the gradient, which tells us which way up and down is, for the current choice of parameters. And then we need to make a change to the parameter to improve it. So what we're just going to do is take a little small step in a downhill direction. So we calculate the gradient to tell us which way is down, and then we're just going to change the parameter a little bit in that direction. Okay. So since this is all a very contrived example, let's say just by chance you happen to choose that white dot to start with as your starting parameter. Calculate the gradient, take a small step. You might see the system going like I've illustrated there with the pink, red dots. Taking little steps down the downhill direction until, luckily, we end up right at the global minimum. We don't usually end up at the global minimum in deep learning, and it doesn't usually matter, really. In fact, it can be advantageous not to do that. But that's all stuff we don't need to talk about. OK, so we had divergence to explain some terms. Let's get back to deep learning. I said earlier, deep learning is supervised learning of parameterized functions by gradient descent. We now looked at what all those ideas mean. A parameterized function is just a function returning a function. Supervised learning means getting some data and trying to fit that data, trying to minimize the error. And gradient descent is a process we can use to minimize that error given a particular choice of parameter. Excellent. So there are a few more choices, a few more decisions we need to make in deep learning. Firstly, we need to say, OK, well, which functions are we going to use? And the choice we make in deep learning is we want something which is a function which is, or a class of functions, because they're parameterized, of course, which are going to be able to express reasonably complicated things, so expressive class of functions. But we also want something that's going to run in a reasonable amount of time. So the choice made in deep learning, something that's well suited to GPU acceleration. The GPUs are orders of magnitude faster than CPUs, as long as you fit their programming model. And in particular, what you would do in deep learning is we normally use tensor multiplication and a non-linearity. So more buzzwords. So let's unpack these things. See what do they mean. What do tensors mean? Well, Tensors are just like a pretentious word for multidimensional arrays. But that's OK, because we're functional programmers. We love pretentious words. Monads, applicatives, all great stuff. And here's a new one to use. So if you have vectors and matrices, you can think of them as 1- and 2-dimensional tensors respectively. And you can go up to 3, 4, whatever dimensions, all just tensors. And an example of multiplication, tensor multiplication is, well, I've chosen vector matrix multiplication because it's much easier to draw on the screen if it's in 2 dimensions rather than 3 dimensions, which is kind of painful to draw. You have some kind of input data, maybe it's a vector, 3-dimensional vector. You have some matrix, 3 by 5 dimensions. You multiply them together and you get an output, which is a 5-dimensional vector. And the parameters here, so a matrix is basically a function, because you multiply by a vector, you get out a vector. You put something in, you get something out. And the numbers inside that matrix, or the weights as they're called in deep learning jargon, neural network jargon, are the parameters that we're going to change. And that changes how that function operates. OK. So the other thing I talked about was non-linearity. And you need this for technical reasons. If you're a sort of statistician type person or in applied maths, if you don't have the non-linearity, the whole thing just turns into linear regression, which is a nice, fine algorithm, but not as expressive as deep learning. So you need this non-linearity. A linear function is basically something that looks like a line. And anything that doesn't look like a straight line will do. So here's an example. What's called the rectified linear unit, very commonly used in deep learning. It's just max of 0 and x. So if x is less than 0, you've got 0, straight line. Yeah, otherwise, you have x. Looks like that. OK, so it's got a kink in it. So it's nonlinear. OK. Putting them together, you get the whole thing. You get a function that looks like this. You've got some input x, which might be the vector we saw previously. You've got some weights in some kind of tensor. You multiply them together. That gives you kind of some value. And then you pass it through the nonlinearity. And that's what's called a layer in deep learning jargon. It's just a function. It's got some tensor operation in, usually, and a nonlinearity. And then putting the deep bit in is just composing a whole bunch of these together, having chaining functions around them. So you get something like this, function composition, which is something that we do all the time in functional programming. Right? Maybe we should change functional programming to called deep programming. It would all be like getting lots of VC money. OK. So one of the interesting things which is happening in deep learning is this kind of move away just from very simple systems, what people are now starting to call differentiable programming. And there are a few things here which are going on. First is there's software frameworks, TensorFlow, Torch, blah, blah. You might have heard of some of them. If you haven't, it doesn't really matter. And the core idea here is this software is automatically calculating the derivatives for us and compiling it all to GPU code. So it's just making it a lot more accessible, a lot faster to write one of these systems and to learn these parameters. And that's a big reason for the success of deep learning. One thing that deep learning models are becoming more complex. It's becoming more like actual programming. And models now have conditionals and loops in them. So this is what caused this term differentiable programming to be coined in the last few months, I think it is. It's becoming more and more like what we do as programmers. You're constructing a program which you think will provide a solution to some problem, but the unique thing here is that part of that program is these weights which you're actually setting based on the data you're seeing. So I think it's a really interesting thing, something that's actually quite accessible to programmers, or will become more accessible as it becomes more and more like programming. All right, so that is the overview of the basic ideas of deep learning. Parameterized functions, gradient descent, so on. Now I want to turn to the core algorithm that makes this all possible. This is what's called automatic differentiation. So we've seen we need to calculate gradients. Once we have a gradient, with the derivative, we can take a little step in that direction. That's quite simple. Parameterized functions, we've seen what a good choice there is. So calculating the gradient is the main thing that we want the computer to do. Great. So we're talking about calculating gradients. So firstly, I want to talk about how derivatives are compositional, which is a really key idea that makes the whole thing work. Then I want to talk about the algorithms for calculating the gradients. And there are two algorithms we'll be talking about. It's called forward mode automatic differentiation and reverse mode automatic differentiation. Forward mode is slightly easier to understand. We're spending a bit more time on that. Reverse mode is a thing you're more likely to use in practice. I'll move that a little bit quicker, but there is code you can go look at afterwards. But first, let's talk about composition of derivatives. So, functions compose. What do I mean by functions composing? Well, we can write something like this. G after f, or g dot f, however you pronounce it, just means applying g to the output of applying f to some input. That's what function composition is. And the really nice thing about function composition is you can build big functions out of small functions. You get little building blocks and you assemble them together, and the process of assembling them doesn't really change the meaning of the individual pieces. Composition is a big deal to us functional programmers. This is why we don't like effects, so side effects, sorry, because side effects break composition. They break compositional reasoning and all sorts of things. I'll rant about that much later if anybody wants, at much depth. Anyway, back to derivatives. The derivatives compose as well. And you may or may not be familiar with the chain rule from calculus. And we can write out the chain rule in this form, which tells us that the derivative of a function composition is the derivative of that outer function g composed with f multiplied by the derivative of f. And what's great about this is you notice that the term in brackets doesn't depend on the derivative of f. It's only when you compose the two things together that you have to combine them. So you can calculate derivatives independently and then combine them. So you don't have to assemble one great big program and then work out the derivative of it. You can break it down into small pieces and compose them together in the same way that you can compose together functions and all the other lovely things we compose in Scala code. Okay, so let's talk about calculating gradients then. All right. So who did calculus in high school or university or something? Okay, most hands going up. Excellent. So somebody said calculate a gradient. You'd probably take what I call the mathematician's approach, which is also known sometimes as symbolic differentiation. And what it is, you'd write down your function, and you get a great big list of rules of differentiation, and you just keep applying those rules until you can't apply them anymore, and then you've got the answer. You were probably tortured with this if you did calculus at some length. The great thing about this is you get an exact solution. You have an expression that is the derivative. You can calculate that exactly. But the thing that's not so great about this is, firstly, that there are no loops or conditionals. It has to be like an analytic function, as mathematicians sometimes call these things. So you can't do these fun things that I talked about people doing in deep learning. It's not really like programming. And there's another problem, which is that the size of the derivative grows exponentially for the size of the expression. This is because of things like this, sum product rule, which is duplicating expressions, not sum rule, product rule. So the derivative can get very big. All right, you'll say, but we're not mathematicians here, we're programmers. Let's take the programmer's approach. Let's hack it, of course. So maybe in calculus as well, you might see something like this, saying you can think of the gradient as being take the function at a particular point, add a small amount onto that point, and then just divide by the same small amount. And this will give you a calculation of the gradient. We're going to have to evaluate the function twice to do this. It sounds like it'd be great. We can do it with any function, good stuff. But the problem is choosing this small amount, this epsilon, is hard. And the error you get depends on epsilon and the function in some very hard to determine way. And you can't really work it out beforehand. You have to sort of do it experimentally. So it's not great. It's not great to get inexact, to get error that we're not really controlling in our calculation of the derivative. So what we're going to do, of course, is the automatic differentiation approach. And I've said there are two main algorithms, forward and reverse. And the advantage of that is it gives us an exact solution, and it works with any function. So it's kind of like the best of both worlds, really. All right, so that's enough hype for automated differentiation. Let's see how it actually works. So we'll start with forward mode, which is simpler. Forward mode automated differentiation relies on this concept called dual numbers. When you first started doing calculus, you might have done that kind of naive infinitesimal calculus, adding on those little epsilon terms and cancelling them out. And at some point, somebody might have told you, no, you're not allowed to do that. That doesn't make sense. And then if you did analysis, you'd have done limits and so forth. But it turns out you can actually do this kind of infinitesimal stuff, and it does make sense in a suitable framework. and that's what we're going to do. So we're going to take a number, a, and we're going to augment it with this b epsilon term, which is our infinitesimal, or our measurement of the gradient. And there's a rule of algebra that for algebra and dual numbers, the epsilon squared is 0. So this is like a complex number where you take a normal number and you stick on this imaginary part. We're just doing the same thing. We're sticking on another part of the number. But in this case, it's this infinitesimal rather than the imaginary number. It has different rules for algebra. So we can implement this in code like so. V is our value that we're computing, and D is our derivative, or our infinitesimal component. All right. Then what we need to do is we need to go and add in rules for basic operations and functions. So adding together two dual numbers, just do the usual kind of algebra here. We add together like the number bits and the infinitesimal bits separately, and we can go and implement that in code, like so. Plus that, the values, the derivatives, add them together. Multiplying together two dual numbers. The usual rules for multiplying together numbers, but you've got to remember that epsilon squared is 0, so we cancel that term out. And we end up with the expression shown on the board. And of course, we can implement this in code as well. And we get that. More interesting is what is the chain rule expressed in terms of dual numbers. So if we have a dual number, which represents this, some computation preceding this, where we've calculated the derivative, the infinitesimal, and the value, and we want to apply it to a function, then what we get is applying the function to the numeric part, the number part, the real part, if we like, and we get the infinitesimal, which is the derivative of the function at this real part, multiplied by the b, the previous derivative. Now, this is the chain rule for dual numbers. And we can implement it like so. So here is the sign, and it looks like that. Now, there's something kind of interesting about this, which is that when we calculate the derivative for sine, we've got two different things. We need to know about the derivative for sine, which is cos, and we need to know about the previous derivative. So we might think at some point, can we factor these out? Because this multiplying by d, this dot d, is always going to be the same. Maybe we could factor that bit out of it. And we'll look at that in a bit, but right now I just want to show you an example. They're just a thought to hold in your head, or not, it doesn't really matter. Okay, so here's an example. Sine squared x, very exciting function. How does the derivative computation work in this case? Well, the sort of control flow would look like this. You put an x, you take the sine of it, two of them, and multiply them together, and you get your result, sine squared x. And when you trace through the dual number, it's going to look like this. We start saying x is 1, and the gradient derivative is going to be 1 as well, because it's constant, y equals x sort of thing. That's our first value. Okay, then we move on to the signs. We apply the chain rule we saw earlier. We get this. Multiply them together, apply the product rule, and there's our answer. And I can copy and paste from a console to prove to you, this is like next level proof here, that yes, this is what we get when we run it. The trace goes through. Now I want to return to manipulation of the chain rule. Any questions on this bit? All good? Okay. I just want to return to the chain rule now and talk a little bit about how we can manipulate it and get something interesting out. So you remember that the chain rule for dual numbers look like this. And what I want to point out here is that the bits that involve A only involve F as well. So we don't need to have, we could think, well, maybe we could sort of pull out these bits and just have some function that you give me A, the real component, and I'm going to give you back the function applied to that real component and its derivative. There's an epsilon that should be at the end here. Could I separate this out? And what happens if I do? And I'm just going to, because this notation is going to get a little bit messy, I'm going to represent a derivative, which is sort of dual number by this box. So what this box means is you've got f of a and its associated derivative. Hopefully that's clear for context. So I can rewrite this code, and we're going to rewrite this expression. We have something that looks like this. So on the right-hand side, we've got what we originally started with. On the left-hand side, we've got some manipulation with it. And what we want to do is somehow, we started with a plus b epsilon. We're going to pass this through f. We've got this one function. And somehow we want to do this multiplying by b epsilon bit that we have there. We want to do some function, implement some functions going to do this. And I'm just going to write a shortcut. Just call this c, this value, just to make it clearer what's going on. Anyone who tell me what is going on here? Did I hear a flatMap? A wild flatMap appears. Yes, it is. It is flatMap. OK, so there's actually a monad here. And there is a monad for dual numbers. It does meet the monad laws. And this monad expresses the chain rule. And we can implement it like so, flatMap, and this does that multiplying by d bit for us. And once we've done that, we can then implement sign as in terms of flatMap, and we don't have to do that multiplying by d bit, repeating it every time anymore. It's taken care of for us by flatMap. OK, I haven't actually seen that mentioned anywhere, so I found that interesting. But let's move on. So deep learning, you need to do the real deep learning, you need to generalize to tensors. I've only shown you the one-dimensional case here. Generalizing to tensors is not really any harder, but it's a lot more work and it gets kind of tedious. So I haven't done it in this case. The other thing that's important to know about forward mode, I haven't really demonstrated here because we're only working with scalars, is that it scales the size of the input dimension. Yeah. And often the input can be quite large, and the output could be like just one number, a decision, yes or no, this is a dog or a cat or whatever. So scaling the size of the input dimension is not great. So let's turn to reverse mode automated differentiation, which is going to solve some of these problems. Who would have thought? Now, the key idea in reverse mode, you probably guessed from the name, is all about doing things backwards. So we saw forward mode went forwards. The key idea is really that the chain rule doesn't really care about which order you apply things. So let me show you what I mean by that. This is our chain rule written out. Just write it out, expanded form. And when we did the dual numbers, we calculated this, the inner stuff first, and then we did the g bit. And math doesn't care which way you do things. So what we could do instead was we could do this bit first and sort of calculate backwards. And what does that actually mean? It means a process like this. You're going to start with our sine squared x again, and you go through it, this time just calculating the real values and storing them in there at the end. And then when we get to the end, we need to go backwards and calculate these derivatives using the equation shown. And you go back, and you go back, and you go back, and you get the result that you'd want. OK, so some complications arise here. The main complication is you need to store the control flow somehow because you need to go backwards over it. So you need to have some kind of representation of the control flow so that you can then calculate backwards down this little graph we saw here. And you can, one way of representing control flow is as a, you want to tell me? Monad. It's a monad. Or you can use continuations, whatever. Doesn't matter. You can represent it as a monad. That's basically what a monad does. A monad represents control flow. And we've already seen that flatMap is a chain rule. So with a different monad implementation, we can implement reverse mode instead of forward mode. And what we need to do is store what I called these k values here. I've got the continuation, and this is what allows us to go backwards. You put a value in and it goes backwards down the computation. All right. This is a fairly subtle point. I don't really want to get caught up on exactly how it works. It'll take me a bit of time to explain. I just want the core idea of automated differentiation to go on. If you want to go in the details, welcome to talk to me afterwards or go have a look at the code. So once we've got this monad, this continuation allows us to go backwards over the control flow. And we can go ahead and implement the rest of the things that we saw and get ourselves reverse mode automatic differentiation. And there we go. We run it, and we get the same answer as before. So you can see that writing the program is very straightforward. It just looks like normal code mostly, but we get this additional calculation of the derivative as we go. The great thing about reverse mode is that it scales in the size of the output dimension, and usually the output is much, much smaller than the input. So reverse mode is the preferred way of implementing automatic differentiation in deep learning techniques. As I said, the code is on GitHub. Don't need to rush your laptop now. I'll show this slide at the end so you can get it. Okay. Right, so we have talked about this idea of differentiable programming, and we said differentiable programming is automatic differentiation. We've seen how automatic differentiation works, and it's about composing code, something that's very familiar to us, functional programming. Now, what's becoming increasingly the case is people are treating differentiable programming as programming. So I want to talk about some of the things which are happening now or in the near future, and just how these relate to programming languages. At this point, I'm getting a little bit speculative. So I'm going to talk about ergonomics, correctness, and performance, how they relate to Scala. So the first thing, ergonomics. We saw that we could write code that looked more or less like this, and it would, with our choice of automatic differentiation algorithm, compute for us the value and the derivative, and it was very simple to work with. Typical systems like TensorFlow, you would write something like this, which is fairly horrendous to work with. In the small scale here, you can probably read it, 3 lines rather than 1, but you can imagine in the large scale, it gets quite painful to work with. So the issue here is you're manually constructing these graphs, these computation graphs, expression graphs, and TensorFlow is not very, it's not very nice to use in the first place, but yeah, it's definitely a problem that people have. The ergonomics are not great. And the solution here is really better DSLs, and of course Scala is great for building DSLs. Really seeing this in Swift. There's an experimental fork of Swift where automatic differentiation is built into the language. So it constructs the graph for you. You just write normal code, and it'll construct the computation graph and run automatic differentiation, and it's very nice. Next thing I want to talk about is correctness. This is quite a big issue. So there are lots of places where you can make mistakes, and people do make mistakes. So a common example is dimensionality of your tensors. You've got to agree. When you multiply 3 by 5 matrix, you get it out of 5, and you have to get all of these dimensions to line up. Another point is that these dimensions usually have some kind of meaning. Like if you're processing images, then you probably have like a red, green, and blue channel. So that's some meaning associated there. And it's very common to do operations which operate over a particular dimension. And when you have code like this, which is the kind of thing you write in TensorFlow, what does axis 1 mean? Is it the right axis? Is that the red channel, the blue channel? I don't know. It's just something, right? So there's a lot of information that's not encoded in the current deep learning systems. And that leads to bugs. And the solution here, of course, is expressive type systems. So expressing the dimensions of the data in the type system, we can do that in Scala, and giving symbolic names to these dimensions, which you can do with type literals, which are something that's relatively new to Scala. But you could do them in inconvenient ways earlier. And that allows you to actually check statically that you haven't made a mistake in the dimensions, and makes a much more readable code because you don't say reduce along dimension 1, you say reduce along the red channel or whatever. Something that's meaningful to you. And so an example of doing this is this experimental package. Nexus is very nice. It's not really a production-ready thing, but I think that's where we can see a lot of stuff in the future going. Cough coming up, excuse me. One more thing I want to talk about here around correctness is I showed you monad implementations before. You can actually write incorrect programs using these flatmaps. And in general, you can write programs that are incorrect, that calculate the incorrect result using automatic differentiation. So it's not just unique to this flatmap. And the AD by itself is not going to, automatic differentiation by itself is not going to tell you things are incorrect. There is other work which is connecting linear logic and what's called the differential lambda calculus to derivatives and that, but I don't think at this point in time anyone really understands exactly how that connects to automatic differentiation. I certainly don't. But I think this might be the way to get more correct programs out. I can talk about this later. I don't want to spend too much time on this because the points are fairly subtle, but if you're interested, let's talk later. Finally, I want to talk a bit about performance. Now, you need compilation for performance, and you need ready to compile to GPUs for most situations, not all of them. So there needs to be some compiler involved. Right now, the way this is done, I showed you, like the TensorFlow is with these embedded DSLs. And these are fairly horrible to use because you have to construct the computation graph manually so the compiler can walk over it and work things out for you, work out the compilation. It's not a great experience. And what we can do in the future, or what's going on now, is staging. So staging, again, is something that Scala does very nicely. There's a tool called lightweight modular staging, which does it, though it is a fork of the Scala compiler. I'm hoping that with what they're talking about in Dotty, staging is going to be a key part of the library, the language. And the idea of staging is basically you have a program which writes a program. And that program itself can write another program. So with staging, you get to create a program which is then going to generate some more code which gets maybe compiled into like the GPU format. Much easier system to use than just having to construct these graphs by hand. An example of what can be done there is this Lantern system, which is Tiak Romp's group in Purdue, I believe. All right. So that was just some sort of looking ahead at where I think we're going. Deep learning is something that's moving very fast. The systems we have right now are really quite primitive. I think we're going to see a lot of work in the next few years in making it better. Is Scala going to be part of that? We'll see. It really comes down to doing it. But let's go back over the conclusions. Firstly, deep learning is all about function composition and derivatives. And we know that functional programming is about function composition. So that's great. We've seen we can easily express derivatives in functional programming. In fact, there's a monad, which makes us inordinately happy. And I think that for what we've seen, the features, the type system, staging, Scala is well positioned to be for the next generation of deep learning system. But it is undoubtedly a lot of work, and somebody's got to do it. And it's probably not going to be me. Though if you'd like me to do it, and you have a big pile of money, then let's talk. All right. So that's all I got to say. Hopefully I've given you enough of an understanding of how deep learning works that you now sort of feel that you can understand it. You can maybe implement it yourself. You know about automatic differentiation. If you want the code, there it is on GitHub. And if you have any questions, that would be great. Thank you. All right. So any questions out there? I've done such a great job. There we go. I got one.
So you mentioned that flatMap corresponds to chain rule. Is there any intuition for what map might correspond to?
Oh, that's a good question. What does map correspond to? I guess map corresponds to multiplying by a like a sort of operation on a constant, or at least an operation on something which is not one of your parameterized variables. So multiplying by like a scalar or thing like that, or otherwise anything that doesn't change the derivative. So like 2 times x, you could implement with map x and then multiply by 2 kind of thing.